Next, we're going to talk about conditional probability. Now, we've already seen that two dependent events A and B, the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Now, the probability of B given that A has occurred is also called conditional probability, and we can denote that as P of B given A. For example, suppose you roll a 6-sided die. Find the probability of rolling a 3 given that the outcome is a number less than 5. So let's say I roll the die and I don't show you, but I take a look at it and I say, okay, it's less than 5, so I know it's less than 5. What is the probability of that die being a 3? Well, we're actually looking for, in notation form, the probability of 3 given that our die is less than 5. And that's how we're going to write it. That bar is pronounced given that. Okay, so this is the probability of rolling a 3 if the sample space is restricted to the number of the set of numbers that are less than 5. So our sample space is 1, 2, 3, 4, and 5. Okay. So how many possible outcomes? Well, there's 5 total possible outcomes, and there's only one 3. Therefore, the probability of rolling a 3, given that I already know that the outcome is a number less than 5, is one choice out of 5. So the probability to roll a 3, given the number is less than 5, is 1/5. And that's what conditional probability is. Another example, let's say you're dealt one card from a 52-card deck. Find the probability of getting a 9 given the card that you were dealt is a black card. So the way we're going to write that is probability of 9 given that my card is black. Okay, so let's say I pull a card and I'm like, what number is it? And I'll give you a hint, it's black. Okay, so me narrowing that down to black hopefully gives you a little bit of a hint. So there are 2 black 9s, the 9 of clubs and the 9 of spades, and there are 26 black cards. So the probability that we're going to get a 9, given the card is black, is 2 out of 26, which reduces to 1/13. All right, let's use a problem with data. So in this particular table, we have the probabilities of a woman in the United States, aged 40 to 49, who had a mammogram. The mammogram tells you if you have breast cancer or not, but unfortunately there's lots of false positives and false negatives. So just because you have a positive mammogram doesn't necessarily mean that you're definitely going to have cancer. There's a possibility that you might not have breast cancer and it's a false positive. There is also a possibility that you have a negative mammogram but you actually do have cancer, and that's called a false negative. So that's what this table is describing. So the first question we have are, what is the probability that a patient has a positive mammogram given that she has breast cancer? So because I know that this patient has breast cancer, I'm only going to be looking in the column for breast cancer. So I have the probability that we have a positive mammogram given that she has breast cancer. I'm just going to shorten that up a little bit. So how many positive mammograms do we have? Well, we have 720 out of a total of 800 patients with breast cancer. So notice I disregarded the whole rest of the table because I know she has breast cancer, so I can only look for the values in the column for breast cancer. Now if I divide by 10, that gets me 72 out of 80, and then if I divide that by 8, that gets me 9 out of 10. So the probability that she has a positive mammogram given that she has breast cancer is 9/10, or 0.9, which is very high. The next question says, what is the probability that she has breast cancer given that she has a positive mammogram? So we know that she has a positive mammogram. So in this particular problem, the only row that I can look at is this blue row right here. All of my numbers have to come from that row because I already know that she has a positive mammogram. So I'm looking for the probability that she has breast cancer given that she has a positive mammogram. So how many people have breast cancer? Given that she is positive is 720 out of the total number that have a positive mammogram, 7,664. And if I divide this by 8, that gets me 90 over, you might want to get a calculator out, 958. And I believe that's divisible by 2 as well. So that's 45 over 479. If I take out a calculator, that's going to be around 0.094. So the probability that she has breast cancer, given that she has a positive mammogram, is 0.094, which is really low. So just because you have a positive mammogram doesn't necessarily mean you have breast cancer. That just means that they probably need to do more tests because there is a large likelihood that it could be a false positive. And this concludes our lesson on events using the word and conditional probability.